Okay, so we're going to talk about network flows. Can everybody see the screen there? Okay. Network flows, a very important, very fascinating topic. Builds upon everything you have studied so far, a basic graph thing, basic BFS, DFS, shortest path type constructs that we have learned. But it's like these many variations. There are like books and books written about network flows, and has a lot of applications, right? So I think other than minimum spanning tree is a very important problem, one of the classic combinatorial optimization problem. But its applications are limited, right? It's an important problem in itself. Network flows is a very important problem, but it has a lot of applications. We will see some of them. And then it has a lot of variants. In each variant, they were defined for many important applications in transportation, in logistics, in freight, in many other optimization problems. Very beautiful topic. In many ways, it's kind of a standalone topic, right? So you don't need much background there. We will appeal to your BFS knowledge, BFS, DFS at some point, but not very, at least today, for the most part today, if you assume that thing, where is the class guy? Is it connected? I don't think it's connected. Can you get, okay, it is. Okay, so suppose you're given a network. So a graph now is a fancy word. We'll use networks. Good reason for it, and I'll be clear. You're given a network, which is, what do you see? Look at this picture. What do you see in this picture? Have you seen this creature before in this course, other courses, discrete math? What is this? What do you see? Directed graph. Yes, what else? Any other feature of this? This is a directed graph, but there are weights on the edges. Okay, so it's a weighted directed graph. There are restrictions on these weights, and we'll talk about it later. But for now, let's assume these are positive integers, okay, non-negative integers. This is, think of it as a network of pipelines. So these nodes are junctures where pipes are plugged in, or these are intersection of road, and the edges are road segments, right? Or pipelines that carry some kind of flow, right? Some kind of fluids or something. And we want to ship some fluid, let's say oil, from this special vertex called S to this one special vertex called T, right? So we want to spend as much flow as possible. That's why it's called the flow network, right? So we have to do flow. So we'll define flow of this thing. Now, here is one way. So there are, of course, some restriction. Otherwise, the problem is meaningless. It's only become important when you have some constraints on it. Two restrictions. The first is, on edge, the number written here is actually depicts its capacity, right? The maximum capacity of flow that can go through this edge, right? So it cannot take more than 2 units of flow. From A to D, this edge cannot carry more than 2 units of flow, right? So this is a capacity constraint. And the next thing is, no node can save oil, right? There is no storage at any node. Any amount of flow that enters a node must go out also. Still natural, meaningful constraints, because we have no storage capacity. Does it make sense? Right? Okay. So, and we want to ship as much oil from the source vertex S to the target vertex T. What is so special about these two vertices S and T? These two constraints, the capacity constraints, no pipeline can carry more than the capacity given, and no node can store the flow inside it. Okay. So now we want to do, why would you need it? As usual, every time we make a pipeline, the S is by the, that's what I'm talking about. What's so special about S and T? These two vertices S and T, what do you see? Yes?
S has no incoming edge, and T has
S has in degree 0, no incoming edges, and
T has no outgoing edge.
T has no outgoing edges. These are called sink node, and T is a sink node, S is a source node, right? Its out degree is 0 for T, and in degree is 0 for S. Okay. So we want to ship flow from S to T, okay, the max flow. Here is how it can, you will see this type of things. What was another thing? Okay. So let's say suppose I send 2 units of flow through this edge from S, A, D, T. It's a path from S to T, right? Any flow has to begin at S and it has to end at T, right? Nobody else can store it. T can store infinite amount, S can generate infinite amount, let's say. So if I ship this flow along this path, flow is it's assigned to edges, but then because of the edge constraint, if I say just ship some flow of 2 edges, 2 units on this edge SA, right, of 2 units, now where is that flow going? Because A cannot store it, so it must go out of from A. So that's why we just say, okay, let's ship a flow across the A path SADT. Okay, these 2 units. This is how we'll write it. Right, so the red numbers are the units of flow going through these edges in this path. Okay, does it satisfy the constraints? Does it satisfy the constraint, this flow, the capacity constraint? Is there any flow across any edge that is more than its capacity? Right, this is 2 less than 3, 2 less than or equal to 2, 2 less than or equal to 2. Right, so the capacity constraints are satisfied. It's clear. Is the storage constraint satisfied? That's called the flow conservation constraint. Is that satisfied? Is there any vertex that takes more flow than it leaves out, that it sends outside, or anything that takes less flow and then send more? Right? There's nothing there. All of them, every edge, every vertex has certain number of incoming flow and then certain number of outgoing flow, and both these numbers are equal except for the one special vertex S and the special vertex T. Does that make sense? Okay. So that's one flow. We can send another 4 unit of flow across this path, right? This path SCET, we can send another thing. Does this flow individually satisfy the flow, the capacity constraints? Does it? Right? So this 4 is less than or equal to 4, this 4 is less than or equal to 5, this 4 is less than or equal to 5, right? Every edge carries as much flow as it has at least that much capacity, okay? And it also satisfies the storage constraint, no storage constraint, right? Nobody can store it. So that's the kind of things we'll study, and we'll formulate the problem after we are able to measure the goodness of a flow, and that will give us an idea about this. Okay, so here is something, for example, these 2 restrictions. This is a flow. Now the questions we have to see, every time, by the way, you have to solve a problem, you don't jump to for I equals 1 to n type solution, right? You study the problem. You ask for what is the motivation for the problems, what are some applications of it that helps you understand the problem. But then you study the problem, okay? You study what are the goodness measures. Say somebody asks you, so this is a true story. At some point we were devising a so-called soft load shedding scheme, and whatever the Pakistani or WABDA type people, they asked me, okay, we have to devise a soft load shedding scheme because these meters are capable of it. So your meters, the automatic meter, AMI stuff, they have the capability of negotiating with the power producer, power suppliers, so the power supplier can actually set up 10 units of flow with it from 3 to 4 a.m. Right? So from 3 to 4 p.m. you will have 10 units of electricity available. Now it's your choice. You can use an air conditioner for the first 10 minutes and then it will be total load shedding, or you can have a light bulb and a fan going on for the whole hour, right? So it's called soft load shedding scheme. And it's a true story when they actually, so in a very formal meeting, they asked, okay, solve this problem. And I said, okay, you have to tell me more about how, and they said, no, there's no constraint. There is a certain amount of production and then there is a certain amount of demand. And we have to fulfill the demand. And I said, okay, anybody who asks for electricity, you should kill them. And it was like, this minister of electricity, what kind of solution is this? He said, told me, solve this generation and the supply and the demand gap. And I told him, all the demand, just kill the demand. And then they had to tell me what is the goodness measure. So any problem that you discuss, you have to actually see what is the goodness measure. How are you going to measure my solution? How are you going to compare one solution and another solution, okay? Without that, it's just you're not studying the problem, okay? So the first thing is, like, it came up with some flow, it's a solution. we have to be able to say, is this good enough? You all agreed that this is actually a valid flow, it's a feasible flow, it satisfies both the constraints. Is it good enough? Is it the best? Is it what the customer wanted, right? We need to come up with some measure, right? Is this the best flow? Then we have to say, that, okay, so if it's the best flow, comparing two flows, for that we need a quantified measure, a numerical measure, right? So what has to be the size of flow? How do you define the size of flow? Okay, and then when we say, then we come up with this, how do you ensure that some flow that you come up with is actually the best possible? Okay, so and we'll come up with this, and that's what we call formulation of a problem. Okay, so I'm going to give you those, so this is some applications that this is used a lot for. So if it's a highway network, then vertices could be intersections, and edges could be road segments, and this could be traffic flow, right? These idiots who designed the underpasses in DHA there, now they didn't see the storage constraint, and Watine choke was choked for a lot of time, and now they're doing this. So flow networks, traffic flow is used a lot, both for the communication networks and actually transportation network. And in many communication networks, vertices, routers, switches could be actually nodes, and their links, wireless links or wired links, are edges, and we see how many packets can flow, what's the maximum number of packets and stuff. And then the pipeline networks, the fluid networks, oil networks, this is the most widely used applications of these things, right? Edge weights are capacities of the link, so physical capacity, physical volume that a pipeline can carry at a given time, or the number of cars in a road can accommodate or something. Okay, so some terminologies, I'm giving to you those more formal numbers for the terminology. Capacity of the edge is the weight of the edge, right? We denote it by C sub E. We assume it's a positive number. It doesn't make any sense for having a pipeline or a node, an edge link that carries negative capacity, right? It has no capacity. So it's a physical number, so we assume it's a positive number, right? Or at least non-negative. The source, this one special vertex S, there will be always in a flow network a vertex that has degree 0. Right, in degree 0, so it's called the source node. Technically, it's called the source node. This generates all the flow, right? And then there is one target sink node that is actually the destination of all the flow. This says out degree 0. Okay, it does not send any flow outside. It just absorbs all the flow. Okay, it consumes all the traffic. An ST flow, a flow from S to T. So now onward, we will not call it ST flow because we are talking about max ST flow. So we'll just say max flow, but there is always a fixed S and a fixed T in mind. There are multi-source flows, there are multi-sinks flow, there are circulations where everybody is a producer, everybody is a consumer, and many other variants of it that I'll mention later towards the end. So an ST flow is an assignment to each edge. What is the number of units of flow going through each edge? That is called the flow, right? So a flow is actually a function from edges, the edge set, to the real numbers, right? So I'm going to formally define it. It's assignment to every edge a flow, right? Remember a function? A function gives every element in the domain exactly one element of the codomain, right? So every edge will get some flow, and that flow will be either a non-negative number, and there will be exactly one number given to it. That's called the flow, right? So it's a function from the edge set to real numbers, so positive, non-negative real numbers. 0 is also allowed. So but this function must satisfy the capacity constraint for all edges and the no storage constraint for all vertices. Okay, so this is a flow. I will write a flow is a function from the edge set to real numbers, but I will denote it by use of notation f sub e. It's not the function notation, f of e. We will write f sub e, meaning the flow on the edge e. Okay. There is a capacity constraints. Every edge has a number capacity. The f number, the flow on edge cannot be more than the capacity, right? It has to be less than or equal to CE. For all edges, this is the capacity constraints, and this is called the no storage constraint. It's also called the flow conservation constraints. The incoming flow must be equal to the outgoing flow for every vertex. Okay, so what is the flow on a vertex? The flow, incoming flow at a vertex. We'll write this as f sub n later. So this is a vertex V. There are 4 green edges incoming to V, right? So the total flow, the sum of the flow on each of these 4 green edges is what we call the incoming flow to V, right? The flow that is incoming to V, right? Technically, we write is all the edges whose second endpoint is equal to V. There, all the directed edges uv, where v is equal to this vertex v, you add up that flow, the sum of those flows must be equal to the total outgoing flow, which is the flow on all the edges where the source vertex, or the, what is it called, the first vertex, the vu type edges, you add up those flows, and that's called the outgoing flow. Right? For every vertex, these two numbers must be equal. Is this clear? So now it's the flow somewhat formulated. I just need to give you the goodness measure. So this is how we define a flow, right? Is it a good flow or a bad flow? That's what we have to define, and then we'll make up a problem of max flow. Any question with the flow network or flow formulation, please?
If the cost or the capacity of edge is 4, and we are like inflow is 5, and the outflow would be obviously 4.
Good.
Is it a correct?
No, so please, that's a good question, but you have to understand the capacity is given for edges. Edges have numbers, weights written on it, right? Through that flow, so in your particular case, you said the word inflow, that was word. If there is an edge, it's a directed edge, A to B. If there is 4 is the capacity, you cannot send 5 there. That's the capacity constraint. For vertices, there is this flow conservation constraint. Make sense? That's flow conservation constraint. For vertices, look at this capacity constraint. The flow through this edge E cannot be more than, this is going to be less than or equal to, has to be less than or equal to C sub E, right? So C sub E is the capacity of this edge E. This is a function of the edges. This statement is about edges. While the flow conservation constraints is a function about the vertices, right? It's the total incoming flow, or all the incoming edges to this vertex, must be equal to the total outgoing flow, meaning of all the outgoing edges from this vertex, the total flow has to be equal to the income. Is this clear? The green flow has to be, the green numbers, sum of the green numbers must be equal to the sum of the blue numbers. Okay, the green and blue distinction is clear, right? Green depicts the incoming edges and blue depicts outgoing edges. Yes, please. Good. So good question. So she says, can't we utilize 2 paths at once? So in the previous example, I gave you one path, added some flow, then another path, added some flow. Good question. We'll see. Right now, our interest is to formulate the problem, to establish the yardsticks, establish how we're going to see which solution is good, which solution is bad. We'll come up with we'll design solution algorithm that's going to be later. Okay, good question. Yes.
For a single edge, the flow can vary between 0 and C sub E for that specific edge, right?
G, please. Yes, for a specific edge, the flow could be any number between 0 and C sub E. Yes, CE. Sorry?
The value of the flow can change as well with the edge, right?
No, so a flow is a number. A flow on a graph is the number on all the edges. So it's a one number, it's fixed. How we come up with, when we design algorithm, maybe we will first say 1 and then later it will say 7 and later we'll make it 19 and sometime reduce it even. So that's what we'll establish, right? But whenever you say you're done, here is the flow, here is the solution. That solution has a value on each number. Look, so in our example, your solution will have these red numbers on some edges. On the other edges, we assume that the red numbers are actually zeros. Those red numbers must be less than or equal to the corresponding black numbers. Okay? Any other question? No, okay. So this is the 2 constraints. So now we're coming, this is, so a flow, please understand this. A flow is actually, so let's say the graph has 19 million edges. A flow is like 19 million numbers. Make sense? Those numbers be such that every number must be less than the corresponding capacity number. And for each vertex, the sum of some numbers that are on the edges incoming to this vertex must be equal to the sum of those numbers that are on the edges outgoing from this vertex. Is this clear? That's a flow. Flow is a function, okay? So I'm asking you to come up with a function, to come up with an algorithm that will do this mapping of each edge will get a number, okay? And that numbers have to satisfy these two constraints. So I'm just, because it's going to be it's difficult to talk about these green numbers and blue numbers and stuff, so let me just give it some words. It's easier for us to talk about. So F out of V is the sum of the flow on all the edges that are outgoing from V. Is this clear? So this was actually for the previous diagram, this is actually the blue numbers. The blue number, okay? The one number, the total flow that is outgoing from this vertex is this guy came late, and now it's my fault to spend another 30 seconds to tell him this thing. No cell phones in my class, okay? So F sub E, F out of V is the sum of the flows on all the edges that have the source vertex is V, okay? F in of V is the sum of the flow of all edges that have the target vertex is V. Okay, so again, this is the blue one, this is the green thing. For a subset of X, now flow is defined on edges. So we wanted to enhance our vocabulary, and we'll talk to the flow through some vertex. So we define the incoming flow to a vertex, the sum of some flow, and the outgoing flow from a vertex is the sum of the flows on the edges, right? We further expand it, and we define the flow through some subset of vertices. Right? Flow through multiple vertices. Again, flow is defined for edges only, okay? But we have now extending our vocabulary. F out of X is the sum of the flow on all edges that are outgoing from X, right? And F in of X for a subset of X is the sum of flow, that is the sum of flow on all edges that are incoming to X, okay? Have you heard of this terminology, an edge incoming to a subset? Have you heard this terminology? An edge is two vertices, right? A directed edge is an ordered pair, X and Y. X is the source and Y is the target, right? Or so X from X it's outgoing this edge, and from Y to Y it's incoming. What is an incoming edge to a set X? I'm sure you have heard this, but I don't want to use the word. In the next slide is coming. What can be an edge that I can call it an outgoing edge from some subset of vertices? Edge is one vertex, right? Outgoing from one vertex, incoming to one vertex. What can be an edge that is outgoing from some subset of vertices? G, please. A cut. In the cut sense, you must have heard this thing, right? If you think of X as a cut, any edge that has the source is some endpoint in X, the source is one vertex in X, and the destination is some vertex not in X complement, that can be called as an outgoing edge from the whole subset, right? And similarly, incoming edge, okay? So the incoming flow, F in of a subset X, is actually the sum of the flow over all the edges that are outgoing from X, right? So this is the outflow from X, okay? And F in of X is the sum of the flow on all edges that are incoming to X, okay? This with some diagram, you can make a diagram. So right now we had this one diagram for one vertex V. If there is multiple vertices U, V, W, right? So there's three vertices. All the vertices, edges that are between U, V, W, we don't care. They are neither outgoing, not incoming. There are some edges that have one endpoint. The first endpoint is U, V, or W, and the other endpoint is some other X, Y, Z, right? Or those which is the source is some A, B, C, and the incoming is U, V, W. That is called incoming edge. Okay, so the sum of those flow. Again, this is just some terminology, so we can talk about it easily. This is going to become very easy now when we establish this thing. Any questions so far with the setup? Okay, these are just terminology. Okay, now the problem. We are given a flow network. What is a flow network? It's a directed graph. So it's a set of vertices and set of directed edges, and a capacity function, an edge, a weight function that is gives every edge some number, some capacity. Okay, we assume the capacity is non-negative, right, or is positive, because if the capacity is 0, we might as well delete that edge, right? That makes sense. If there is a pipeline that can carry 0 traffic, we might as well ignore that from any consideration, right? Any road that cannot take any traffic, what's the point of just writing it? Okay, so that's why in that sense technically it's correct that I wrote that the capacity is a positive number, but it's generally supposed to be a non-negative number. Okay, and there is a fixed vertex, well identified vertex called S vertex, and it's a source vertex, meaning its in degree is 0. Okay, and there is a fixed vertex, well identified vertex distinct from S, that is a that's a sink vertex, meaning its out degree is 0. Right? So this is the input, the numbers are given, the thing is given. The demand is that we have to come up with a flow. A flow is just a function from edges to the real numbers, positive real numbers. A flow is just coming up with the numbers on each edge, right? But that has to satisfy the two constraints. One is the capacity constraints. No edge can have flow more than its capacity. No edge can also have a negative flow. That's also a requirement. 0 is less than or equal to FE is between 0 and CE. It's clear? And the flow conservation constraints. For no vertex can have incoming flow more than the incoming flow at every vertex has to be equal to the outgoing flow from that vertex. Okay? Clear? That's the requirement. Now, what is the size of the flow? We have to define just now the goodness measure. Size of the flow, it's very natural we define, is the total flow in the system. Okay, the total flow in the system. Now note that total flow in the system is just a big word, but at every vertex, whatever flow comes in, that also goes out, right? In net total flow that goes out is actually what comes out of S, right? So the total, the size of the flow we define to be is the outgoing flow of the vertex S. What is the incoming flow at S? What is Fn of S? What is the number Fn of S? What? 0? Why?
Because it's the source vertex.
It is the source vertex, so why it has to be 0? There is no incoming edge to S, right? So there cannot be any flow to it, right? And those two vertices S and T are allowed to have to violate the flow conservation constraints, right? They can't do, remember this thing, the flow conservation constraint is for all vertices other than S and T, right? So if 19 units of flow comes at T, in comes at T, there is no edge out, so it cannot go out, right? Otherwise it just cannot be solved. The problem is not well defined, okay? So we define the total flow of the graph of the system. The total flow is to be the total the outgoing flow from S. Right? The incoming flow at S is already 0. And that must be equal to the incoming flow at T. Does it make sense? Please understand this thing, that F out of S must be equal to F in of S. This must be equal. These two numbers must be equal no matter, as long as you come up, if there is a valid flow, meaning satisfying the two constraints, then F in of S must be equal to F out of S. Does it make sense? So let's say 19 units of flow is incoming at T. Can it happen that F out of S is equal to 17? Why? Because where is the other 2 units of flow coming from? All the vertices, they do not generate, they do not store, cannot do, whatever they come in, they take in, they just send about. Right? So if there is 19 incoming flow at T, there must be 19 flow generated at, there cannot be 17 units of flow generated at S, right? And the vice versa, if there is 19 units of flow incoming at T, can S generate 21? Then where did this 21 flow went, right? Where did it go? No vertex can save it, T didn't take it, so where is it? Right? It cannot, very simple, you can just write it algebraically, and we will do it later. It's a very simple, natural thing to deduce from the two constraints, right? From the capacity constraints and the actually not the capacity constraint is not needed, from the flow conservation constraint. Is this clear? So that number, that magic number, f out of s and the f in of s, f in of t, these two we make them as our objective function, right? These two numbers, or this one number, we make it our goal, right? We call this the size of the flow, and we try to optimize that. We try to come up with some assignment of flow to edges such that size of f is as large as possible, right? And that's why it's called the max flow problem, right? So find such a flow which satisfies these two constraints and such that size of f is as large as possible. Is this clear? Is the optimization problem now clear? Any question? Okay. Now, can you think of an application of this, like something? Can you think of applications? So you have a pipeline network, let's say from some place in Karachi, and then you have some destination in Lahore, right? So this two oil depots, and then there are multiple pipelines. You have to decide how much flow to send through that pipe, how much flow to send the other pipeline, which routes, right? They may share at some point, they may join at some point, in this kind of, that's the application, and we want to maximize the flow, right? To send the maximum thing. We'll see many more applications of this later. This is for me. Okay, so having formulated the problem, now we'll start to think about solutions. So this is our problem, okay? The first thing, again, we are not solving the problem yet. We are trying to see how to say which flow is good, which flow is not good, right? So look at this. Look at this cut. I want to come up with an upper bound on the flow, right? I want to say the flow cannot be more than that, right? Something like that. This will give us a good thing if I'm finding a flow, right? The moment I reach this upper bound, so there is no further hope, I would stop working on it, okay? So this is a cut. You remember a cut? It can be a cut technically is just a subset of vertices. We picture is that subset of vertices and the complement. So this is what we call a cut. And this is how we depict a cut, right? Pictorially, we show this sort of edges that are actually cut. One endpoint is on the left side, the other endpoint is on the complement side, right? So this is a cut. On the left side, it contains the vertex S, and on the other side, the complement contains all other vertices, including T, okay? Now, let's say there is a flow of, any flow that I generate from S has to go through one of these three edges, right? These cut edges. Does it make sense? If S generates whatever number of units of flow, it has to go through these edges. Is this clear or no? Yes? So, can there be a flow in this network which has weight more than 3 plus 3 plus 4, which has total size more than 3 plus 3 plus 4? Can S generate, what is 3 plus 3 plus 4? Huh? 300? What is 3 plus 3 plus 4? 10. Can there be 11 units of flow in this network? Why not? Just argue this. Everyone knows this answer to this. We have talked about it. How would you argue this? How would you describe this constraint in this upper bound in Pashto? Quickly. Sorry, is this Pashto? I don't. Why is it 10? Yeah, that's what I'm saying. Yeah, but that's good. That's fact. But why does it? How would you explain it to a 5 years old that there cannot be more than 10 units of flow in this network? Yes.
There's no edge to carry the extra one.
Who has to carry?
There's no edge to carry the extra one.
Yeah, so that's kind of essentially a proof by contradiction. These are unspoken proof. Every one of us know it, right? Nobody is expecting you to be able to write it formally. But think about it. Suppose there is 11 units of flow. Well, the SA edge can take 3 units, SB edge can take 3 units, SC edge can take 4 units, and that is, you guys told me 10, so who is taking the 11th edge, right? Who is taking the 11th unit of flow, right? So S may generate it, but it cannot reach T, right? The size of S is defined, the size of flow is defined to be the edge, the flow on SA plus SB plus SC, right? And those numbers cannot be more than 3, 3, and 4 respectively. Is this clear? So that gives us an upper bound. This cut gives us the capacity of this cut. Capacity of the cut is the sum of the edges that are out crossing, right? So the capacity of this edge gives us a upper bound on the max flow. Yes, please.
Could the flow be like parallel, or does it have to take only one path? Like, does it go through?
Oh, it could be many. It could be many. So we define float is whatever you give write some numbers on these edges which satisfy those two constraints. Then this is no edge, no path.
It would be like 2 paths from S to T.
Yeah. So earlier I gave you example. Remember that was a path, the upper path and the lower path. There was at least 2 units on the top path and 4 units on the lower path. Yes, this could be this thing. So examples are coming. Yes, please.
Wouldn't greedy like solve this?
We will see. We are not interested in solution for now. We are just interested in upper bound of this thing. Okay. So solution is always very easy. So my least favorite topic. You will see that I will finish in three slides. Okay. Never ever jump to solution. That is the useless thing to do. In algorithm design, what I tell always people, you bother the problem. You just work with the problem. You find one case, another case, good case, bad case, easy case, right? You just bother the problem, then the problem will tell you, okay, here is a solution, please leave me alone, right? That's how you do it. Never ever talk about solutions, okay? That's a boring thing, useless thing to do. Always talk about solution. Always think about problems. Okay, so what was I talking about? You made me talk about solution. Okay, so any flow that I generate from S has to go through one of these 3 edges. Hence, the sum of these 3 edges gives me an upper bound on this thing. So there cannot be any flow of size bigger than 10. Yes? Here is another cut. This is also a cut that has S on one side and T on the other side, right? Which edges are going from the S, this set SABC? This SABC is the cut, right? Or SABC in conjunction with its complement, which is DET. This makes a cut. Or if you draw it like this, any flow is generated on the left side of this diagram and goes to the right side of this diagram, right? Now, can there be a flow? What is this 2 plus 1 plus 1 plus 5? So this is also a number. What is 2 plus 1 plus 1 plus 5? I can't do arithmetic. Can never do arithmetic. It's 9. Okay. So previously we had a 10 thing, right? Can there be a flow in this network of size more than 9? There cannot be a flow of more than 9, right? Why? Because let's say there is a flow of length 11, right? Of size 11. So max AD can take is 2 units. Max BD can carry is 1 unit. Max CE can take, what did I say? Who did say 9? Where is 9? 2 plus 1 is what? 3. And 3 plus 5 is what? Is it 9? 8. Just 8. So not 8, 9. Okay. Those are the edges going from the set, this cut C to C complement. So if there is any flow that goes from S to T ultimately, AD can take only 2 units, BD can take 1 unit, and CE can take 5 units. So there cannot be any flow, and I'm going to prove this formally later, that this is a bound. No, there cannot be any flow more than 8 in this graph. Make sense? In this network. So we got earlier a bound. We said no flow can be of size more than 10. Now we got a bound, no flow can be of size more than 8. Which one is a more useful piece of information? Yes, please. We'll see. We'll see. So let's say we got one bound, upper bound of 10, and we got another upper bound of 8. Which one is a better bound? Which one is a more useful bound? So suppose I tell you no flow can be of size more than 19 million, which is true about this graph, right? Is that a useful piece of information? Right? It's not, because you will have a flow of size, let's say 8, but you still will have to try, because your upper bound is 19 million, right? There may be. So this is a better bound. It's a tighter bound. Whenever you have an upper bound, you want to reduce it, right? You want to reduce it as much as possible. You want to improve your solution, and you want to reduce it. It's a maximization problem, right? Upper bound, the tightest upper bound is the best. Okay? If you have a minimization problem, the tightest upper bound is actually the highest, right? The lower bound has to increase and increase. Okay, so we got another bound. Any other question? This is a really strange view of the class. But the same is true for any cut. So apparently I cannot even spell stuff. Not only arithmetic is not my only limitations. There cannot be any, it is true about any cut. So here is another cut. This is also a cut that takes S on one side and T in the complement. Its weight is 2 plus 5, right? The capacity of the cut is 2 plus 5. Now I'm claiming there cannot be any flow in this network of size more than 7. Okay, this is a better bound. It's also true because whatever flow has to is generated at S, ultimately it end up at T. To end up at T, it must use either the DT edge or the EF edge. Okay, so if this number there cannot be more than 7 units of flow through this two DT and ET edge. That's why the total flow cannot be more than 7. It is also a bound, right? Better bound than the 10 and the 8 one. This is a better bound. We don't know if it's the best bound, right? So we will see that thing. So this is the bound. So we can assume that, okay, if you're going to do this, if you're going to design algorithm for finding the max flow, 7 is you should not hope for anything better than 7. That's the first thing, okay? That's what we got. And so now we're going to do like the more tight, and actually later tomorrow we'll prove that it's actually the best bound. So an ST cut, right now you have heard the word cut, right? Cut is a subset of vertices and we think of the complement of it. We now call it ST cut. All of the 3 cuts I showed you here have one feature in mind. S was in one set and T was in the complement, right? That's why we call them ST cut, where S is in the subset, and T is not in that subset. That cut is called an ST cut, right? It's clear? How many ST cuts are there in a graph? You have a graph on n vertices. How many ST cuts are there? This is another thing. Whenever you hear a construct, you hear a definition, right? The first thing you should do is, what is its value? What is its max possible value? What's its min possible value, right? What's its good values, bad values? How many, if you want to understand ST cuts, the best answer, the best way to do it is how many cuts are there? That's a good thing. How many cuts are there? A cut is a subset, right? What's the largest possible cardinality of an ST cut?
N minus 1.
N minus 1. Why not n?
Because then that won't be a cut, it would just be the entire graph.
It will be a cut, but it will not be an ST cut. If you remember the cuts thing, a cut is a subset of vertices. It could take all the n vertices. The other side is empty. It's a trivial cut, but nonetheless is a cut, right? But for it to be an ST cut, it could be as big as n minus 1 because it cannot contain T. It could be as small as 0 because then where is S? S is also with T then, right? It has to be the minimum possible size of an ST cut, the cardinality, let's call it, because size of cut has to do with the edges crossing. The minimum possible cardinality of a ST cut is 1. The max possible cardinality of an ST cut is n minus 1. Okay, the count, the combinatorial complexity of the cuts. How many cuts are there? How many total cuts are there in a graph? Not ST cuts, just cuts. Again, just linguistic. A cut is a subset of vertices. So how many cuts are there? 2 raised to power? Yeah, n, right? So we said n vertices. So it's 2 to the n is because it's a subset. Any subset makes a cut. How many ST cuts are there? 2 raised to power? Why? No, again, look at the definition. What is an ST cut? This is not a quiz question. This is just directing your thought process there, right? A ST cut is a subset of vertices that contain S but not T, right? So it's a subset of the n minus 1 vertices, right? So it's going to be 2 to the n minus 1. except for 2 to the n minus 1, that number contains the empty set also. That counts the empty set. So it's 2 to the n minus 1 minus 1. Okay? Or any subset of the n minus 1 vertices except for the empty set. So it's 2 to the n minus 1 minus 1. Okay? 1 less than 2 to the n minus 1. Is this clear? That's the number of ST cuts possible in the graph. Some of them are good, some of them are bad. We'll see that later. Okay? So this is an ST cut. We understand it. It's a subset of vertices A which contains S but cannot contain T. That's the definition of ST cut. Okay? What is now we define capacity of an ST cut. The capacity of an ST cut is equal to the set of the sum of the capacity of all edges that are outgoing from the cut A. Okay? What are these edges that are outgoing from the cut A? Which is, these are directed edges. The source vertex is in A and the target vertex is not in A. Those are called edges outgoing from A. Okay? These edges are called outgoing edges of A. If I add up the capacity of all these edges, that is called the capacity of the cut. Okay? So this is going to, so the diagram is in the next slide. The capacity of an ST cut clear? ST cut is clear, and the capacity of an ST cut, it's just the word we define it because capacity was defined for edges only, right? Now we defined it for set, for cuts actually. Okay? We earlier also we say flow was defined for edges only. It's a function of edges, right? But now then we extended it to function of vertices and the incoming flow and outgoing flow, and then we defined it for flow of subsets also, right? Outflow of subset and inflow of subset. So this is the capacity. It's nothing to do with flow, right? It's, you give me a graph and a cut, I can tell you what is the capacity of that cut. Okay? In these two diagrams, in the three diagrams here, what is the capacity of this cut? What is the capacity of the first cut, the cut given in the first diagram? Huh? That, what are the crossing edges? What are the edges that are outgoing from the cut containing the set S? Yeah, these three edges SA, SB, SC are outgoing edges from the cut. What are the incoming edges to this cut? None, right? It's empty S. It's only contain the vertex S, which has no incoming edges. So it's, and the capacity of this cut is 10. That was the number, that 3 plus 3 plus whatever, right? 4. What is the capacity? What are the outgoing edges from this cut? The second one. What are outgoing edges from this cut? AD, BD, and CC, right? CE, right? These three edges are out. What are incoming edges to this cut? D to C, right? This one edge is incoming, right? How about the edge SA? Is it incoming or outgoing? It is inside the cut. It is not either incoming, not outgoing, right? It has nothing to do with the exterior A complement. Okay. So the capacity of this cut is whatever 2 plus 1 plus 1 plus 5 or 2 plus 1 plus 5. The capacity of this cut is 2 plus 5, right? Those are the outgoing edges from this cut, DT and ET. These words clear? Okay. So we define the capacity. Now we're going to prove this theorem. This, I gave you a demonstration of this with these three examples, but this is always true, right? You come up with any flow as long as it's a valid flow. It satisfies the two constraints, the capacity constraints for each edge and the flow conservation constraint for each vertex other than S and T. That flow has, and for any cut, come up with any ST cut, not any specific, the three specific I drew, there were very few of them. I told you there are 2 to the n minus 1 cuts. For any of this cut, this is the true statement that the capacity, the flow, size of that flow must be less than or equal to the capacity of the cut, right? Does it make sense? The question makes sense? It's a very natural statement. The one you just said, you told me there cannot be any flow more than 10 in that graph and more than 8 and then more than 7. But there is a formal proof, and that's not just mechanical proof. What is the size of the flow? Size of the flow we define to be the outgoing flow from the vertex S, from the source vertex S, right? Or the incoming flow at the sink vertex T. Let's say F out of S, that's the size of flow. The size of flow is F out of S plus I'm adding this stuff, right? For all other vertices other than S, you add the incoming flow minus the outgoing flow, right? All other vertices in the cut other than S, right? I'm just adding these formula. I'm adding this equality holds. Does this equality hold? This equality? Why is this why does this equality hold? The flow conservation constraint. Why does this equality in the first line, the second equality in the first line hold? The first equality is actually a definition, right? It's not equality, it's just how we define. This is an equality, it's a numerical equality. Why? Yes?
The summation will be 0.
Yes. So we are just adding, so I've written here the comments, the argument, we are just adding a bunch of zeros. Why are these numbers 0? Why is the summation 0?
Because the amount of flow outside the node is equal to the amount of flow inside.
Which node?
Anything. All the vertices.
No, not all vertices.
Except S.
Except S and except T also. But in this case, we are talking about A. These are vertices in A only. So T is not in A, right? T is an ST cut A. A complement is an ST cut. So we are just adding a bunch of 0. Equality is not violated, right? Why is these two outgoing flow equal to incoming flow for all vertices other than S and T? What is the word we gave it? The flow conservation constraint, right? Is this clear? So now look at this. Now I'm just writing, this is the summation, linearity of summation. The sum of A plus B is the sum of A plus the sum of B, right? So I just write that thing, F out of S plus the first term plus then the second term, right? Negative sign. What is this thing? F out of S plus the sum of F out of V for all V in A. This is all V in A except S, and this is S, right? So this is just basically n plus 1 terms there, A plus cardinality of A plus 1 terms there. So I'm just writing that cardinality of A 1 terms here, F out of A. Make sense? Exactly the same equality. And the other one also is all the outgoing flow from the cut A to A complement, which is just equal to the it's the incoming flow at all the vertices of A except for S. But I wrote here all the incoming flow at all vertices of A. How many terms are here in this summation? Let's say A has k elements. How many terms are there in this summation? K minus 1, right? S is not there, no? A has S and k minus 1 other elements. But here, how many terms are here? This is all the incoming flow for all the k vertices. Why is this true? Is this clear? Let me please understand this thing. It's very mechanical. This is one term, the outflow of one vertex. This is the outflow of k minus 1 vertices. And this is the inflow of k minus 1 vertices. But here I've written the outflow of k vertices, S and all other A, and the outflow of all the k vertices, the inflow of all the k vertices. There are 2k minus 1 terms here, and there are 2k terms here. Why are these two equal?
Because the source is not coming.
Because f in of S is 0. There is no incoming flow at S, right? That's why we spend time on that. There is no incoming S flow, so it's just adding a bunch of zeros. So it's true that there are 2k terms here, but the term I just added is 0. Okay? So this is f out minus f in of A. Now we're going to use just the definition of f out of A. What is f out of A? It's the sum of all the flows that goes through any edge that is outgoing from A, right? So it's the E outgoing from A is Fe. This f in of A is the sum of all edges, the sum of the flows over all edges that are incoming to any vertex in A. That's how I wrote the sum of all flows over all the edges that are incoming to A. Okay? What do I know about the flow, any flow on some edge? Fe must be less than or equal to Ce, right? So this thing must be less than or equal to the total capacity of all the outgoing edges from A. Is it clear? Each flow of this sum, each summed in this sum must be less than or equal to the corresponding capacity. So it must, the sum must be less than or equal to the sum of the capacities. Okay? This I leave it as it is, right? Now I'm claiming that this is actually equal to the capacity of the edge. This is equal to the capacity of the cut, right? So this is less than or equal to, this size of f is less than or equal to the capacity of the cut. That's what we wanted to prove, right? Look at the block, size of f must be less than or equal to capacity of the cut. Did we get that? So this is the formal proof of the diagrams I gave you, that the flow must be less than 10, must be less than 8, must be less than 7. That comes from this theorem, right? The theorem is very simple, but this is very important thing we are going to talk about. All we got is an upper bound on the flow. No flow can be more than any of the cut's capacity. Come up with any cut, the flow has to be less than or equal to its capacity. Is this clear? Okay. So I'm going to use this thing to the, how many of you know duality? You did discuss duality somewhere, right, in the class? No? You didn't discuss duality? Nowhere? Seriously? Where would have you discussed duality? Okay, so this is the first duality, and I was specifically told by Dr. Mudassir to discuss the dualities, but we will do the first. Duality is a really cool word, okay? You can impress a lot of people with this. You have to learn this in order to market yourself, that you say, oh, that's for the max flow min cut duality theorem that tells you, right? It's a max flow min cut theorem. Duality it's a good tool, a good mathematical tool to look at a problem from another side. Okay, so essentially something like this, that if I ask you to find the max of an array, right, that is equivalently to find the minimum of the negation of that array, the negatives numbers of this array. Does it make sense? That's kind of, in one side you are maximizing something that's equivalent to minimizing another quantity, and that quantity is the dual of that, right? So then there is a huge thing, it's called the primal, the dual. There's a huge story of the primal dual algorithms, right, that gives you a huge amount of things. The algorithm we are going to discuss is actually going to be the prime dual algorithm without that terms. Later when we do approximation algorithm, you will see the primal dual theorem, okay? The first duality, max-min duality, right? One makes, it's a cool thing, really cool thing, not fancy. It's a simple concept, but really, really useful, okay? And so what we got is actually something close to duality, right? Here is, we proved that this, give me any flow and any cut, right? The flow, size of the flow must be less than or equal to the capacity of the cut. Okay? So for any flow and any cut, any ST cut, any ST flow and any ST cut, the size of the flow has to be less than or equal to the capacity of the cut. But it's also more importantly that generally I told you earlier that we want to come up with the tightest upper bound, right? The smallest upper bound. The smallest upper bound will come from a cut which has the minimum capacity. Is this clear? So we saw the flow was less than 8, less than 10, less than 8, less than 7, right? 7 was the better cut. If I give you another cut in that graph whose capacity is 6, then the flow has to be less than or equal to 6 also, right? So that's the thing. If I have a cut, this is called the min cut, right? Out of all the ST cuts, this cut has the smallest capacity, okay? So this theorem says the size of any flow has to be less than the capacity of any cut. So the size of any flow has to be less than or equal to the capacity of the minimum cut. Okay? So this is called, the size of f is less than or equal to the capacity of this minimum cut, right? This best cut, the optimal cut. Okay? And later we will see that this is actually, there is an equality between them. So we'll see that the max flow, look at this thing. The size of any flow is less than or equal to the capacity of the minimum cut. So can I say the size of the max flow is less than or equal to the capacity of the min cut? Any flow you can come up with, it has to be less than this C, right? So the largest flow also will have to be less than or equal to this C. So the max flow is less than or equal to the min cut. This is called actually the max flow min cut theorem. Later we'll prove that these are actually equal. Okay, and this gives us a very good algorithm for the cut. So now we have this thing. Now let's just do one quick construct. So I'm going to continue these sessions on max flow. It cannot be done in one session, but I gave you enough now vocabulary, enough terminology that you can think about it. Algorithm is very easy. I told you to max 3-4 slides with 2 algorithms actually, in total 4 slides. They will be covered. And then a lot of applications of this thing, okay? So the max flow, we got this thing. So far we got this thing that the size of flow, any flow has to be less than or equal to the capacity of the minimum cut. We defined flow properly. Now we are going to do a greedy algorithm for the find a flow, a good flow. Somebody mentioned greedy algorithm earlier, right? Was it you? Somebody was voting for greedy algorithm earlier, no? Why are you ashamed? It was a very good attempt, a very good start. We actually am going along your advice. Who said the greedy algorithm would work? You said that, okay. Okay, so by the way, if people have tried, there is no known algorithm for max flow that is basically a divide and conquer based paradigm in that paradigm, or the dynamic programming strategy. There is no need for that because we have a very good algorithm for it, but there is no known. The greedy algorithm works quite well for this. Okay. The algorithm is extremely important. It gave us this whole LP dualities. It gives us that's called the simplex algorithm for linear programming. This is actually this algorithm, but there it's termed more in lines and algebraic terminology. This is more of graph theoretic terminology. Okay, so we start with the zero flow. That's always the best thing when you do greedy algorithm. Let's start with the flow of size 0. What is a flow of size 0? What is the flow? A number on every edge. So if I put the number 0 on every edge as the flow, is that going to be a feasible flow, a valid flow? Why not?
It's negligible.
Huh?
It's negligible.
It's not feasible? Why?
It's the same as having no edge there at all because you can't send anything.
No, so it's a valid flow. No? Nobody can see it. It doesn't violate any constraint. Does it violate any capacity constraint? Because all capacities are greater than or equal to 0, 0 is less than or equal to 0, no capacity constraint. Does it violate any flow conservation constraint? No, because the total incoming flow at every vertex is 0, no flow is generated, so nobody got any flow, and nobody sent out any flow, so the incoming flow of every vertex is equal to the outgoing flow of every vertex, right? So it's a valid, feasible flow. It's not a good flow, it's not an optimal flow, but it is a flow. Okay, so we begin with the 0 flow, and then we start to improve the 0 flow more and more. Okay, how do we improve it? We find a path from S to T. That's why you suffered a lot through BFS, DFS. That's why you suffered through Dijkstra's and Floyd-Warshall's and whatever other you did. You guys did Bellman-Ford algorithm, right? You find a path. In this case, I didn't say find a shortest path, but find a path from S to T and send flow along that. Okay, you have to bear with me for some time because I have to do this thing. Suppose it's a graph, just for the sake of understanding. Assume all capacities are equal to 1. That's why I didn't write anything, right? The directions are there. And suppose I send a flow through this path SADT of unit 1 unit flow, SADT, right? So I started with a 0 flow. This is a 0 flow. And then these three numbers at these 3 edges I incremented by 1. Okay, is this a valid flow? Is this a valid flow? Okay, does it violate any capacity constraint? Does it violate any flow conservation constraint? Can it violate, please understand this thing, can it violate the flow conservation constraint at this vertex C? Previously C had 0 incoming flow and 0 outgoing flow. Now also C has 0 incoming flow and 0 outgoing flow. Okay, can it violate the capacity constraint on this edge? Capacity is 1, the flow is 1. Can it violate the flow conservation constraint at this vertex A? Previously it was 0 incoming, 0 outgoing from A and to A. Now, what is the incoming at A? And what is outgoing at A? 1. So, at all A, D and T and S, these constraints don't apply on them, right? Those are special vertices. Is this clear? So, this is a valid flow of total. What is the total size of this flow? The one I drew in the graph. What is the total size of the flow? Total size of the flow is the total outgoing flow from S. It is equal to 1, right? And total incoming flow at T is also 1, so that's the size of the flow. Can I improve that flow? Can I come up with a better flow? Still valid, still feasible, but higher size than this. Which one is that? If I send another unit of flow through this path, let's say S, B, F, and T. Okay? Again, this is a valid flow. No capacity constraints are violated. All capacities are 1. All flows are 1. Right? No conservation constraints violated at C or E. No conservation constraint violated at D or F also, because then F also gets 1 unit of flow and it also went out. Right? This is a critical point. You understand that we are not just adding randomly some numbers on the edges. We are adding flow along paths. That is the first vertex from S and the last vertex is T. Can I add another unit of flow across this path? S, C, E, F, S, C, E, T. Yes? I can add another unit of flow. No constraints are violated. What's the total flow here in this graph? What's the total size of the flow? 3. Why 3? The flow on this edge plus the flow on this edge plus the flow on this edge, and that's 1 plus 1 plus 1, right? So it's 3. Is it the best flow? Why is it the best flow? Because any flow has to be less than or equal to 3. This 3 is this magic number for now. 3 is the capacity of a ST cut, this ST cut, right? So it is less than or equal to 3, and it has to be less than or equal to 3, and I have it equal to 3. So this must be the best flow. Okay. One quick extension to this. Let's say I modify the graph a little bit. Just that was too toy a case, right? All capacities are equal to 1. Here is only one edge whose capacity is equal to 2. All other capacities are equal to 1. Right? I'm going to start with a 0 flow. This is a 0 flow, no red edges. Let's start add capacity through the path SADT, capacity of flow of size 1. Okay, this thing. Is it a valid flow? This is a valid flow. No capacity constraints are violated and no conservation constraints are violated. Can I add more flow in this graph? Where is the more flow? Through the bottom path, right? I can add this flow through the S, C, E, and T path, right? Let's call it the blue flow. What's the total flow now? 1 red, 1 blue, so it's 2, right? All valid flow, right? Can I add any more flow in this through this in this graph? Where is the flow? Which? S, B, D, and T, but will be 2 unit flow going from D to T on the DT edge. Is that okay? There will be 2 units of, if I send the green flow also, flow along the green path, does it violate any constraint? Does it violate any constraint? How much flow is going through the DT edge? How much flow is going through the D to T edge? 2. 1 green and 1 red, right? Does it violate any constraint? No, it was 2 was allowed in this thing. Is this the best flow? This is also the best flow because look at this cut. There are 2 cuts. They cannot be cut here, cannot be more than 3 here, more than cannot be less than equal to 3 here, less than 3 here, because I found a flow. Flow has to be less than equal to cut. Okay, so I'm going to start doing this thing. This is not for arbitrary reason that it was always violated. This is a cool thing. Whenever I add flow through a path, it will not violate any constraints if I keep the flow size less than equal to the so-called bottleneck. Okay, so let's say I have a weighted path from S to T. Bottleneck is the minimum weight, the minimum capacity of any edge on that path. Is this clear? This is called the bottleneck, right? The one that is a troublemaking edge, right? The min edge. Is this clear? In this path, if I send a flow of along a path, then no flow conservation will be violated. That has nothing to do with bottleneck. Any flow that is sent through a path, the first vertex is yes, the last vertex is 3, no flow conservation will ever be violated. Why? Because in a path, every vertex has one incoming edge and one outgoing edge. Whatever flow is coming in, that same flow is going out, so there will be no violation. But if I add a flow, another thing, if I add a flow along this path whose size is no more than the bottleneck of the path, then no capacity constraint will ever be violated. Does it make sense? Okay. If I send here a flow, let's say B is the bottleneck, right? The number B is actually the minimum capacity of any edge in this path. If I send B units of flow along this path, previously we just saw that no flow conservation will be violated. This says no capacity will either also be violated. Can somebody claim that some edge is now some flow or through some edge is more than its capacity? I added B units of flow along this path. B is the minimum weight, the minimum capacity. Can some edge have their capacity constraint violated? No. So can somebody say that here this was 10 capacity and you are sending 12 units of flow? Why can't we send 12 units of flow? Because B has to be less than or equal to 10, right? B is the minimum. So I'm sending minimum, no capacity constraint will be violated. Okay? Make sense? So these two facts actually ensure that if I start with a zero flow, and as long as I add flow through paths from S to T, then this will going to be a good flow and keeps on increasing. If you can find a path from S to T, you can keep on increasing the thing until you cannot find a path. Is this clear? All of us know how to find path from S to T. How do you find path from S to T? You run a BFS from S is a source vertex, and if you hit T, that gives you a path, right? So everything is ready for us in our toolbox. All the ingredients that we need to come up with this, to complete this greedy algorithm is there. There is only one issue. This is last. I'm done with today's slide. There is only one issue. I have to somehow make sure to know that this path has already been used, or this path is no more available, right? Or some fraction, some capacity of this edge has already been used, and what is available, that is just, and we'll tomorrow come up with a linguistic tool to talk about that, right? So in this case, so look at this, in this case, so I did this thing, I sent through one path from S, A, D, T. I need to keep it in the record somewhere so that next time I find a path from S to T, it's not that top path, right? And in this particular case, because I have sent a unit, so I need to keep a record that the next path cannot send a 2 units flow through this edge, right? Because part of that edge capacity has already been consumed through the previous path. The keyword here is what's called the residual network, right? That is just a bookkeeping tool to find out when you keep on sending flow through a path. Find path, send flow. Find path, send flow. That's the algorithm. We know how to find path. We know how to send flow. Is just incrementing some numbers. But just keep track of these numbers should never go violated. And this will not violate. One addition of one flow will never violate. I just proved that. But all of them in combined should not violate, and that's just the residual network enables us to do this. Tomorrow we'll finish the algorithms, 2 algorithms actually, the Edmund Kopp algorithm and Ford-Fulkerson algorithm.